Nice. Today I will talk about the quantum field theory from the A to the Z with the best explanation. So there are too many topics. I will talk about many things today. So okay, just with blue pen. Okay. So I'll start with the classical field theory. First of all, I will define the field and constructs of the Lagrangians and the quantizer of the field as a field of point. And I'll talk about the fluid theory and go to the interaction theory, and I'll do how can we obtain the Bellman diagram and the example with the QED process. And after this, I will turn to the some higher spin 1/2 and the spin 1, and go into the path integral formalism. And after that, I will go to the loop diagram and the normalization, and after that, I will go to the non-abelians group theory and the finals. I will talk about some symmetry and the symmetry breaking with the anomaly. So there are too many things. I will explain the best speed. So first of all, talk about the classical field theory. The particles are described by the fields operator. The fields is the physical quantity defined through the space-time, and this field will become operators in the quantum level. And by using the field, we can construct the Lagrangian density and action. Such action is minimized all the stationary action, and such a both quantities are large invariant scalar. So the action defines as the integration of the Lagrangian density over the space-time. And by using the stationary actions, we can obtain the Lagrangian equations for the Lagrangian density, partial phi, and the partial mu phi and partial mu, such a form. So this determines the equation of the motion. So the point is, if the Lagrangian is given, then we can obtain the dynamics of the field. And the similarity to the classical mechanics, in the Lagrangian Hamiltonian, we can define the Hamiltonian density. The field conjugate momentum defines like that. The derivative of the Lagrangians above the pi dot here. And the Hamiltonian density can be obtained by the Legendre transformations. That is the same. So here's a two example. First of all, we can describe the real scalar field. This is a kinetic term in the relativistic version, and this is a potential term as a mass term, and there's a no additional interaction term. So this is the free field theory. And by using the Lagrangian equations above, so we can obtain the equational motions following one. And Hamiltonian density is the following. And for the complex scalar field, there is a 2-degree freedom real part and an imaginary part. So for the Lagrangian density, and we can obtain the Hamiltonian density. And one more careful things is there are two concepts, the conjugate momentum, because of the 2-degree of freedom, capital phi and capital phi daggers, complex conjugate one. And briefly, I want to talk about the symmetry of the Lagrangians. The symmetry means that the Lagrangian density is invariance in the transformations, and by the Noether theorem, there will be always the conserved quantity. And so there are two concepts of the theorem here. First of all, we can consider the field transformation, and another one the space-time transformation. For the field transformations with the small deviation delta phi, we can define the t times delta capital phi, where the t is a parameter, and the Lagrangian changes like that, and actions still changes. Then the Lagrangian density changes given by the such a partial W mu system, which is total derivative. And by the integration part, we can obtain such a form, and this term and this terms disappear by the Euler Lagrangian equation. So the point is the total derivative term and this term, the combination of the two terms conjures if we define the inside of this term as another current. And we can obtain the conserved charge by the integration of the J0, the time component path of the Noether current. And the second form of the Noether theorem is the symmetry under the space-time transformation. And among under the such transformations, we can obtain the field transformations and the Lagrangian changes. And similarly, we can obtain the conserved quantity, which is trans energy tensors, defined like that. The indexes are given by the mu and the nu here. and the 0, components correspond to the energy, and the 0 components correspond to momentum, and the ij correspond to the momentum flux. For example, if we consider the complex color fields with the U1 symmetry with the such pages for the pi and pi dagger, and then we can obtain the Noether theorem for the transformations. So this is the Noether current here. Next, now we return to the previous quantizations. So far we discussed the classical field theory. So we define the field and construct the Lagrangians and discuss about its symmetry. But now we will turn to the quantum version. If we review the quantum mechanics from the quantized to the from the classical level, there's the operators level. So in the classical mechanics we describe the displacement, but in the quantum mechanics there's operators. This is the separated state, and then there's the quantum mechanics. There is a canonical conjugate relation between the position x and the momentum p. Similarly, so we can quantize from the classical field theory to the quantum field theory. The quantum field theory is actually the combination of the partial relativity theory, which is the unified space-time x mu, and the quantum operator. So the field which defines the space-time, so changes to the operator's level and satisfy the canonical conjugate relations, which is this is the field conjugate. And for the free fields, we know the exact solutions. The all free field has a following form, which is Helmholtz equation form, the space-time propagations and the mass phases, and by the Planck transformations, we can describe as these equations in the momentum space with the pi p modes, and for the each p mode, we can find the solution as a plane wave form for the Helmholtz equations, and that is satisfy the following relations with the analysis and the momentum relation and the partial relativity theory. Then such equation motions are very analogous to the quantum spatial harmonic lattice, which can be defined as the creation of operators and annihilations of operator. So the operator x and p's that is clarifies the creations and annihilation operator a dagger and a, and the energy eigenvalues are quantized in here. So similarly, so we can construct the field operator here pi x. So this is the field is described by the combinations of the ladder operator I plus and I at some specific momentum mode, and that there will be the p mode plane wave solutions multiplied, and the field operators at the x is given by the momentum expansion or the Brent transformations form. So to specify the field quantizations for the operator level, so defines like that. The field operators at x is defined by the summations of the mode p mode with the ladder operators at the momentum p and the prime wave mode as a Brent transformation form. The first terms correspond to the creations of the particles with outgoing ones, and the second terms correspond to the annihilations and the ingoing particle. And also we can define the field conjugates operator pi correspond to the p in the quantum mechanics. And the commutator relations between the field and the field conjugate satisfy the canonical conjugate relation here. And this is the spatial relativity theory, so that it should satisfy the causality. The commutators are balances at the space-like separations of the event. And also we can define the Hamiltonians with the expansions of the a plus and a, and there will be some vacuum energy fluctuation. Such field operators can be interpreted as some creation of particle. If we X the field operators on the vacuum space, then there will be the corresponding the particle appear. And there are such a two factors appears by the Lagrange invariance. Some remark. And similarly, we can do the periodic conjunctions for the complex color. In this case, the something difference is that there are two ladder operators, A plus A and the B plus, because there are two degrees of freedom. So the canonical conjugate relations, so there are two forms. And for the Hamiltonians and the Noether current, we can also those two quantities can be expressed by the two kinds of the ladder operator. And for the Noether current case, the ladder operators B plus and the B correspond to the antimatter, which gives the minus electric charges. And now we will define the propagators by using the such build operators formulations. The propagator is actually the two-point correlation functions. If there are two fields acting on the two vacuum, then this means that these propagators connect the one space-time x1 and the other one x2 by the build. And there should be the time ordering in here. So this is the definition of the Feynman propagator. And by using the build quantizations, inserting this pi and the pi x1 and the pi x2, we can obtain the Feynman propagators in the momentum space. And there are some other calculation process by using the control integrations through the complex variable and the larger theorems at the pool, then we can obtain the Feynman propagators in the momentum space. There are two cases when the T1 is lighter than T2, or T1 is equal to the T2 to consider the causality with the special relative theory. And there will be some to analyze the pool and the latitude. There will be some control to both considering the such causality. For example, for the pole equal to the p0 is equal to the minus EP, there will be the r epsilon to avoid the pole. So such epsilon means that the virtual particles in the off shell. And so that there are the results, the propagators in the p space, this one, I over the p squares minus m squares plus r epsilon. Here's one thing I want to mention is here such a p case is not real on-shell momentum. This is off-shell particle, so that this is not same with the m case in here. And these propagators can be interpolated as a green function, sort of the given equation of the motions in the mathematical point of view. So far we discussed the classical theory and the quantum theory with the free Lagrangian, but now I will turn to the interacting theory, including the interaction term in the Lagrangians. Now the interaction terms will be added, and we want to discuss the n-point correlation function. It means that there will be the n external build from the outside. And the quantum mechanics, there will be the interaction picture. The Beer's operators originally described as Hagen-Barker pictures with the time dependence of the operator, but we want to turn to the interacting pictures, which is expansion is known. So here is the transform from the Hagen-Barker pictures to the interaction pictures for the Beer's operator, and the unitary operator for the time evolutions is given like that with exponentials of I Hamiltonian dt here. And this can be expanded by the such a form. And the third one is the vacuum state. So far we discussed the free vacuum, but we should describe the interacting vacuum. And this interacting vacuum can be approximated to the free vacuums in the time go to the minus infinity to the infinity. So the such n-point correlation functions with the Hagen-Barker picture builds things on the interacting pictures can be rewritten by the interacting pictures builds operators in the time evolutions operators and the free vacuum. So this is the distance expansion. So the point of this expansion is the endpoint correlation functions in interacting theories. They can be related by the endpoint correlation functions in the interacting pictures with the time evolutions factors acting on the free vacuum. So the such time evolution factors gives interacting term. So if we expand this order by order, and if this interacting terms is extremely interacting term includes some small coupling, then we can expand this order by order through the perturbative limit. So now, if we consider one some specific perturbative term, then there will be the in the interacting Hamiltonian includes some several field as interacting term, and such a field that is described by the lattice operator. And by using that, we can obtain the there will be some n numbers of the fields operator which can be represented by the lattice operator. But we can decompose the endpoint correlation functions with a product of the several propagator, which are 2-point correlation functions. So that the point is the endpoint correlation function can be decomposed of the multiplications of the many propagator. So to do that, we will consider some of the ladder operator level. There are two kinds of ordering. The first one is the normal ordering. All the creation operators go to the left, and all the annihilation operators go to the right. And the time ordering is the all the lightest operators, timely light operators go to the left, and timely before operators go to the right for the causality. So the operators ask the time orderings to the some specific state. And the why we consider two kinds of ordering? Actually, we ask the operators with the time ordering for the causality, but for the convenience, if we consider normal ordering, then if that normal ordering is that acting on the valves, then it automatically gives the zero. So the physical system is given by the time ordering, but we want to describe as normal ordering. So there are time orderings and the normal ordering, and there will be some deviation. So if we act on this the right hand side, so this gives just a zero, so that we only consider the deviation. So this deviation is called the contractions, and these contractions actually go to the propagator. And there is a weak theorem. If we convert from the time ordering to normal ordering of some specific combination or status of the vessel operators, then there are some deviations that are given by all the possible contractions. So this is given by the multiplications of the propagator. So so there will be some if we remind of the Dyson expansion. Here, this was endpoint correlation function, so this is the external field, but in the time evolution factor, there will be the internal field. So the propagators between the internal fields, the contraction between the internal fields gives the propagators, but the propagate contraction between the one external field and the internal fields gives the external field. So this gives the Weimar diagrams for the interacting theory. So actually the particular physicists that want to obtain some observable quantity. This is given by the S matrix, the amplitude from the initial state to the final state. So from the S matrix we can obtain the amplitude, the probability amplitude from the initial state to the final state, and if we scale this one, this is the proportional to probability, and this gives a cross section through all the decay light. If we integrate the probabilities over the phase space. So this is observed quantity in experiment, and this is such as matrix determined by the sum of the theory with the given Lagrangian, so that we can test some of the specific theory by this observable quantity. So this S matrix can be obtained by drawing the Weimar diagram. So the S matrix, we can define the Lorentz impedance amplitude M. And for example, the theory is given by the pi 3 theory is as example, and if we consider 2-point correlation functions in here, then the order of the G scale in mind that there is such a form. For the expansions of the exponential factor, that gives the g-square 0 by 6 and the order of the g-square. And there are the two external build and the 6 multiplications of the internal build. And there are, if we consider converting from time ordering to normal ordering, then the remaining deviations is the contractions of the all possible one. So this corresponding that, for example, the x1 and x2 represent the external build, but x and the y represent the internal build. So this one, the contraction between the 1 and x gives external build, 2 and y also external build, but the x and y this give the propagator, and all the other ones are all the same. And there will be some combinatorics factors which comes from the positive number of such contractions as the combinatoric one, and the symmetric factor, the number of the internal operator changes. Here's a calculation, and for the order of the string also we can calculate a similar thing. And only the disconnected part ones just cancels out with the denominators for the normalization, so the connected ones are remain. Also, there are similar examples for the Yukawa interaction. If the theories are given by the coupling between the one's color fields and the two fermion fields, and if we consider ball-point correlation functions and the order of the g-square, then the ball external build, and because there are two fermion fields and one pi in here as Yukawa interactions and the order of g-square, so such a form. And if we consider all the possible contraction between them, then this gives the STU channel, and we can draw sort of bimonodal corresponding that. And also there are some of the consider the last formula, but what it gives in here. So far we discussed first of the classical field theory, the second one sort of the quantizations of this, and second third we go to the interacting theory, but this one is all the for the scalar field spin geo. So now I want to develop the spin 1/2 as the spin 1 as the higher spin 1. Such a higher spins arise from the Poincare symmetry, which is a space-time symmetry, including the translation, rotation, and the Lorentz boost of the space-time. This is given like such a form, and the generalized form there will be the rotations one and the translation one. And such a generators satisfy the following commutative relations, so-called the Poincare algebra. And we can also define the spin of this generator, and the combinations of the rotation and the boost are such Lorentz groups algebra. So is approximately similar to the two multiplication of the S2. So this is algebraic point of view, and then we discuss that in detail in the supersymmetry video. And the point is such a Poincare algebra, there is a custom operator which is all the commutative with all of the varieties. This represents sort of the possible eigens or the representations of the Poincare algebra. So one is the master and the other one is spin. So the spin is the one representation of the such a space-time symmetry, and among that the half into the spins is quite interesting. For example, especially the spin, which is spin 1/2. The spinors are always associated with the gamma matrix about the space-time symmetry, sort of the such a spin observed. The gamma matrix defines with the such a bipolar matrix, whereas sigma is a polar matrix in here, and satisfying the following anti-commutator and the commutator relation. And the Lorentz transformations of the spinors is given by the following generators, which is arising from the commutator relations of the gamma matrix. The point is how the spinors objects transforms under the Lorentz symmetry. First of all, the gamma matrix satisfies the following relations, where the S is the Lorentz transformation here, and the spinors transforms like that. So if we define adjoint spinors psi bar as a psi gamma and gamma q, then there's such a psi bar and psi behaves like Lorentz scalar. Because the adjoint spinors has the transforms behaves like that. And also we can define the transformation of the Lorentz factor psi bar gamma psi here. So also we can define the several quantity by linear covariant as a possible objects by by using the several spinner. But only will discuss the psi and psi bar, psi bar gamma psi as the Lorentz factors to construct the QED, and the Boltzmann interaction also the some of the gamma pi factors will be included, but I will not discuss it here. So similarly, we can consider the spinner build quantization, like as a scalar build quantization. The Dirac-Lagrangians are given like that. So this one, psi bar, partial mu, psi bar gamma mu psi, such a psi bar gamma mu psi, be epsilon the Lorentz factor, so we can define the connected term, and this is the mass term, and we define such a factor. This reduces the Helmholtz equation. And one thing different is for the spinor pairs with half integer. This satisfies the anti-competitive relation, but calculated and another is bounded below. And here's the field quantization, canonical conjugate relation, Hamiltonian, and the charge by the ladder operator. And one thing also different is the Bauman propagating. There will be some P slash C, which is the P mu gamma mu, arising from the spin sum. These factors are the propagated for the spin of wheels given by the I over the P slash minus tau. And similarly for the factor build with the spin 1, we can define the following Lagrangian density. This is the kinetic term and the mass term and the current. This is called the build strength, F mu as a partial mu A nu minus partial mu I mu. So we can obtain the equation of motion here. There's a mass terms and the current. For the massive case, the equation of motions always the fixed gauges. So the by acting the one more time derivatives on the equations of the motion, gauges are always fixed, so like such a Lorentz gauge pi nu a nu equal to 0. So originally there was the 4 degree freedom for the factors, but the 1 degree freedom is died by the gauge fixing, so only the 3 degree freedom remain, and this corresponds to the 3 polarization for the massive factor build, but there must the last case. There was only the 2 polarization, and the 1 gauge freedom, and another one is just die. So also we can define sort of the Bell conjugation and the Hamiltonian density here, and the Bell quantization for the factor build. There of the polarization factors will be added, and the canonical conjugate relations in here. And the propagators by the polarization summation in the numerator, such forms appear. And for the mass last case, there will be no such a term, mass. So by using the such a spin 1 half build and the spin 1 build, we can construct the QED Lagrangian like as a contemporary theory. So D is the covariant derivative, which includes an interacting term here. This is an interacting part. And here's the QED Bauman rule, like as particle physics for the fermions and the photon, and the propagators for the fermions and the photon and the vortex given by the QED coupling. And there are also some remarks, some of the scalar QED can be defined. That was given in here. And by using Born approximations, the such propagators can be replaced by the potentials by using the Brunton formation. And if there are massive vector field, this corresponds to equal potential on is behaves in the very short ranges, but must last one. The long potentials arise, which means that both acts on the very infinite long ranges one. This is the constant with uncertainty principle. So then we discussed the first part of the contemporary theory, and the next I will turn to the second part of the contemporary theory.